Hi guys, we are going to look at some level 2 chemistry today. Acids and bases is the content that we are focusing on, and now this is a year 12 chemistry standard, so not the year 11 one, which was much easier, and not the year 13 one, which would be much harder. Okay, so just let's get started with this. So as a year 12, you would have learned in NCEA level 1 that acids. So what is the definition of acids? So these are substances that will donate H pluses, okay, that will donate H plus ions when they react. And what are bases? Bases are substances that will accept H plus ions. Okay, so we are looking at what we call the Brown-Stead-Lowry acids and bases. There are two types of definitions for acids and bases. We only look at one of them, which is the one we're looking at up on the screen right now. The other one is looking at electrons, and you don't really learn that in NCEA. Okay, so so this is slightly different. This is probably a little bit different to what you did in year 11. So in year 11, you probably looked at this. In year 11, when you know something is acidic, that's because it has lots of H plus ions, and then in bases, it has a lot of OH minus ions. But year 12 now, we can do a little bit better than just that, and we are going to look at these two definitions. So I'm going to give you some examples. So for example, let's use some acids that you used last year, HCl plus water. Now, this is a strong acid. You learned this from last year. The strong acids are your hydrochloric acid, your sulfuric acid, and your nitric acid, which are your common examples from year 11. And we're going to use HCl here. So by definition, HCl is an acid. So what does it do? It's going to donate one of the H pluses, which it only has one. It's going to donate the H plus away from the HCl. So you don't have HCl anymore, you only have Cl minus. And where did the H go? The H went on to the H2O. So instead of having two H's, now I have three H's, and it has a positive one charge because I have one more H than I had before. Okay, so this is what we call the HCl dissociation. So the HCl is what we call completely dissociated in water. Now, we don't want to use the word dissolving, because dissolving, dissociated in water. Dissolving is kind of like, when we're talking about a solute or solvent, but when we talk about dissociation, it's kind of like trying to find a word for it, like disintegration. Like say, disintegrated, like say the HCl split into two. It split into the H plus and Cl minus ions, and then the H plus went to hang out with the water. Okay, so let's give you another one. Let's give you, like say, for example, another acid, like say HNO3. Why don't we use this one? So same thing, HNO3 is, again, it's a strong acid. What does it do? It's going to donate one of the H pluses to the water. So it's going to form NO3 minus and H3O plus. Okay, so now we're going to do a little bit better. Now we identified this as the acid because it donated the H plus. Okay, so that by definition, the HNO3 is the acid. The H2O is actually, in this case, a base. Okay, so this is a base. So what it did is that it accepted the H plus from the HNO3. So that's by definition, it is the base. Okay, so now we're going to look at these two species here, because if you look at the HNO3, I'm going to highlight them. If you look at the HNO3 and the NO3 minus, they're very, very similar, but they're different because they're different by one H plus. And where did the one H plus go? The one H plus was given away to the base. So if the HNO3 was the acid, the NO3 minus is what we call the conjugate base. Okay, so you have HNO3 and NO3 minus, which is what we call the conjugate acid and base pair. So they kind of like, they're a couple, and it doesn't really matter. The concept is somewhat important in year 12, but it's a lot more important in year 13, because when you have to learn more calculations and stuff. But just for now, you just need to understand, yep, if I started with the acid, then I'm going to form the conjugate base, and if you started with the base, this is going to become the conjugate acid. Okay, so your water and H3O plus is going to be the same thing, conjugate acid base pair. Now the conjugate acid base pair, the two species only differ by 1 H plus. Okay, so if you look at these two, they differ by 1 H plus ion. If you look at these two, they differ by 1 H plus ion. The one with more H pluses, the one with more H plus is going to be the acid. The one with less H is going to be the base. Okay, so this can be the same, can be said the same way with bases. Like say for sodium hydroxide. For sodium hydroxide, I don't even bother with the water. They just completely dissociate. It's a lot easier without the water. Actually, they just dissociate into the two ions, and it's exactly the same thing. And they dissociate in water, and then you form you just break them into the ions, and this is how we know that sodium hydroxide is an alkaline. Why is that? Because you will dissociate, because this will dissociate in water and produce a large concentration of OH minus. Whereas before, like say, with the example that we did previously, just to show you, oops, not getting that. So HCl is acidic. Why is that? Because of the dissociation, and then you created and produced a high concentration of H3O plus. So when you have something that's acidic, this is the same as last year, year 11. When you have this higher concentration of H3O plus versus OH minus, this is going to be acidic. When you have more more hydroxide ions than your hydronium ion, this is going to be basic or alkaline. Alkaline is a better word. And then if they are the same, that means you have a neutral solution. Okay. There you go. All right. So that's kind of what you did last year, except we just added in the dissociation stuff. You just need to remember the definition and just go with that. Okay. So that's the first part. But now you are year 12 now. You learned equilibrium. So we are going to look at weak acids and bases. Okay. So for example, organic acids. Oops, can't spell. Organic acids are weak acids. And you may go, what is the difference between a strong acids and weak acids? The most obvious thing is to do with the pH. Okay, so pH, and then later on we're going to do the calculation. But essentially, what pH is just looking at how much the concentration is for the hydronium ion. Okay, so that's what pH stands for, potential of hydronium ion. The more concentration there is, the stronger the acid, the lower the pH. Okay, but if something is a weak acid, so that means the weak acids, only weak acids and bases, they partially dissociate in water. Okay, so what that means is that they don't fully dissociate. Like say, for example, if we go back to our, I'm just going to do another one here. I'm just going to use the same example. Let's say if I have HCl dissociate in water, this is going to fully dissociate. I'm going to make these things. Let's say, for example, if I have 1 mole per liter of this, I'll make 1 mole per liter of the Cl minus, and I'll make 1 mole per liter of the H3O plus. Let's not use moles per liter, let's not use moles, because by definition, because we might be changing the volume, but the mole doesn't change. It's kind of like if you are writing with a pen, you know, if you're taking notes, if you're writing with a pen, if you have a pen that has a lid on the top, so think about the pen. If I break that pen into two parts, you know, the one with the pen and one with the lid, for every single pen that you break, you will make one with the cap and the other one with the pen itself. Okay, so you produce equal amounts, and that's what strong acids do. They completely dissociate, so at the end you don't have any HCl anymore because it's completely gone, and then you have produced equal amount of Cl minus and H3O plus, and they will be in very high concentration because of the complete dissociation. However, if you have weak acids, weak ones, let's say for example CH3COOH, which is a weak acid, organic acid, that's ethanoic acid. This is where, you know, a lot of people go, oh, I suck at organics, I'm not going to bother with it, I'm not going to bother learning it. Well, here it is, it's going to come back and haunt you again. This is a weak acid, so again, by definition, acids donate an H plus ion. So this is where you need to think about the functional group. This is your functional group, and for those of you that are not so confident with organic, this is CH3COOH. This is the functional group, and it is always going to be the functional group that does something. Okay, so in this case it's going to be the H from the COOH that's going to be donated, so this is given to the H2O. So what you are going to produce is that you will make so that's gone, you make CH3COO minus because you lost the H, and then you have transferred that to the H3O plus. Now the key thing here is that this is an equilibrium because of the partial dissociation. So what it means is that if you put the weak acid in a certain amount of water, the water is only going to be able to dissociate a tiny percentage of that, and then the bulk of the solution will still be the original weak acid. They won't dissociate. So like say for example, if I give a, you know, use the same example, if I had a mole of this at the beginning, I probably would make 0.01 mole of this and 0.01 mole of this. So at the end, I will have 0.99 mole of that. Okay, it's about 1 to 5% of the weak acid or base that will dissociate, and then once they have reached what we call saturation, you know, no more can dissociate anymore, then you have established an equilibrium, so no more can dissociate. Okay, so this is very, very important, and this explains why a weak acid, like say for example, we'll talk about this a little bit later in later videos, but this is why a weak acid will have a lower rate of reaction compared to a strong acid, because of the concentration of the H3O plus. Okay, because as you can imagine, you know, with the example that we had previously, if you look over here, I think I rubbed it out. I say if I bring out that example again, if I have HCl, you know, if we look at the strong acid, and this is why, you know, if I have 1 mole of this, if I have 1 mole, they'll dissociate 1 mole and 1 mole of this, I don't have any more of these left at the end because this is completely dissociated. Can you see, can you look at the concentration of these two? Can you see this, the H3O plus concentration is going to be a lot higher than the H3O plus concentration of a weak base, of the weak acid. So that results in two different things. Because of the partial dissociation, okay, so here's a little flow chart. So weak acids partially dissociate, and as a result, you produce low concentration of H3O plus, okay, and low concentration of the other thing, which we don't really care. So low concentration of H3O plus, which means that you're going to be having a higher pH compared to your weak acid, strong acid, apologies, and because of the low concentration of H3O plus, you are going to have what we call a weak or a poor conductor of electricity. Poor conductor of electricity. Okay, so why is that? It's because your weak acids or weak bases, they partially dissociate. So let's find another example. Let's just whip out another example. Let's say if I have NH4 plus compared react with H2O, this is going to give away one of the H's to become NH3 plus H3O plus. Okay, actually this is not the base example. Let's scrap that. Let me just use a longer acid, I suppose. This is actually a good conductive electricity, so it's not the best one. I'm just going to use another carbon, just chuck in another carbon. So for example, this is exactly the same thing, just one extra carbon on there. This is going to become CH3COO minus plus H3O plus. So this has donated the H over there. So as you can see, at the end, the concentration of CH3COO minus and the concentration of H3O plus are going to be very small, are very low. Okay, so what that means there are very few free moving ions, very few free moving ions, hence poor conductivity of electricity. Okay, so because what is, this is where you're going to realize that all of the chem standards are going to add up. All right, so conductivity is something that you did in 2.4 in the solid section. So when you have the solid electrical conductivity depends on the concentration of free moving ions, and when you have a partial dissociation like this, you are going to produce a very low concentration of these, which means you have a poor conductivity. Okay, so that's a weak acid, and weak base are exactly the same. And this is going to be your most popular example, which is NH3, ammonia. So this is gonna accept a proton or H plus from the water to produce hydroxide. So again, the NH4 plus concentration and OH minus concentration are going to be low, are going to be very low due to partial dissociation. Okay, so due to partial dissociation, and then this results in two things. The pH is going to be lower than the strong bases, and then it's going to also have poor conductivity. Okay, so with strong acids and bases, this is really, I hope it makes sense. Like say some questions they could do, like they could give you like say HCl, NH3, CH3COOH, and then KOH. I say these are 4 solutions, and they give you 4 pHs. They give you pH equals 1.2, 4.8, 9.5 and 12.8. I say for example, and they go right, which one's which? Then you need to be able to go right. Well, this HCl is a strong acid. This is a strong acid. NH3 is a weak base. That means it's going to have higher pH than 7, but not that high. Then CH3COOH is a weak acid, which means it's going to have a higher pH compared to your stronger acid, but still lower than 7. And then your KOH is going to be a much stronger base, which means it completely dissociate to give you a 12.8 pH. Okay, so that's some of the questions that we can elaborate and practice later on, but this is the concept that you have to be able to understand. Now, before we wrap up, this is something that's going to be the most challenging part for this section, so I'm going to do this multiple times, but here it goes. This is the first type. All right, so well, the only type because you only get 12. Now, if you did organics, or if you somewhat still remember organic, this is sodium ethanoate. Okay, so this is a salt, like sodium sulfate, sodium nitrate, sodium chloride, you know, the salts that you get from year 11 from acid plus base give you salt and water. This is a salt. Now, how do we determine this pH? And you may go, all right, if I tell you what one is 5.8, one is 8.9, I say which the pH is one of them, Is it 5.8 or is it 8.9? How do you decide? Like, how would you figure it out? So this is the part where you need to actually show what we're trying to do here. You first need to understand that your salt, like your table salt, when you put this in water, you will dissociate. You'll break down into the two ions. You break into, so you just split them into the ions. So you have this, and the CH3CO and A will be gone because it completely dissolved. Okay, so this is not dissociation anymore. This is like dissolving. You have the solid, you chucked it in water, then it's gone because it has dissolved. So you made the ethanoic ion, then you made the sodium ion. And then from what we've done previously, you should be able to identify, like, hold on a second, if I make CH3COO minus, and I know I have a bit of water, this will continue to react to produce CH3COOH plus OH minus. And then the moment you see OH minus, this should tell you that you have a base. Okay, and then when you you need to be able to write the equilibrium yourself, but then hopefully you see this examples more enough, then you're gonna be like, all right, CH3CO minus, all right, CH3COH. These things are the weak bases or weak conjugate acid that you would have seen so many different times. And then hopefully you remember this is a partial dissociation, so you're gonna remember this is the pH is going to be 8.9 because you have a concentration of hydroxide, partial dissociation, so 8.9 seems about right. Okay, so the OH minus concentration. So first of all, a few things happened. So we're gonna do a little summary here. So the CH3COO dissolved. Okay, and produced, and you have produced high concentration of CH3COO minus and high concentration of Na plus, and then the CH3COO minus further partially dissociate into into CH3COOH and OH minus. Okay, but the concentration of OH minus is going to be low, hence the pH will be above 7 but not too high. Okay, so I'm just trying to simplify it here. All right, so this is looking at the pH. Now the other thing that we need to emphasize on is electrical conductivity. Now when you have a salt, this thing is actually quite a good conductor. If we look at this, why is that? If you go back to what we talked about before, this CH3COO and they completely dissolve, and you have high concentration of that, you have high concentration of Na plus, and then yes, this CH3CO minus further partially dissociated, but then you still have heaps of this, and you still have heaps of that. So conductivity wise, this is a good conductor. This is a good conductor of electricity due to high concentration. The Na plus doesn't do anything due to high concentration of CH3COO minus and Na plus, which are free moving. Okay, so this is what we can, something that you could, need to, we'll definitely revisit this and go through some exam questions. Okay, let's just, before we go, one more. I'm not going to write too much about this one. Like say for NH4Cl, then we go, all right, let's look at NH4Cl. What can we talk about? So first thing first, NH4Cl. First of all, let's split it, dissolve it into the ions. And then once you dissolve it into the ions, you're going to be like, hold on a sec, this NH4 plus, I've seen that before in the previous section. This is going to further partially dissociate into NH3 and then H3O plus. And if you don't know if it's H3O plus or OH minus, just look here, it's going to donate that away. So it's going to pick up the extra H. So when you see the H3O plus, so you're going to know this solution, this pH is going to be acidic. okay, but kind of like 4 to 5-ish. All right, so that's what you're looking at. 3 to 5, 3 to 6 could be all right. And there's also a electrical conductor. Okay, because of the, why is that? Because of the high concentration of those NH4 plus and Cl minus. Okay, so I hope this makes sense. This is kind of like an introduction lesson, and then we will go through some more questions, like detailed questions later on. Okay, so hopefully this has helped you, and I'll see you guys next time. Bye bye.